Okay, continuing with Chapter 6, Section 6.4 on friction. So here's a picture of a shoe which is pushing on a wooden floor, but the shoe is not slipping. So on a microscopic scale, if you were to somehow zoom in, here would be the shoe and here would be the floor. Even if they look smooth, they're actually rough. The shoe has all these points sort of hanging down, and the floor has all these mountains sort of pointing up. And so there are some points where the shoe and the floor are actually in contact and little molecular bonds form. Okay? And now if the shoe is being pushed towards the side, these little bonds can produce a force that is tangent to the surface, so left to right here. And this is called the static friction force. It's a result of many of these little molecular springs being bent or compressed or stretched ever so slightly. So on a big scale here, if you have a box that is being pushed but it remains at rest, that's due to static friction. Okay, so here's the free body diagram. There's a normal force in the box from the floor pressing up. There's gravity on the box pulling it down. This woman's applying a pushing force towards the right, and so there's a static friction force that's responding towards the left. And static friction force is equal to this pushing force. And it points in the direction opposite to the way the object would move if the surface were slippery. So static friction acts in response to an applied force. So especially on a horizontal surface, if there's a pushing force to the right, the static friction is to the left, and it balances out and causes the object not to move. As the pushing force increases, the static friction grows until it gets to F sub s max, the maximum static friction force. Now, if the pushing force gets any bigger, the object will start to move. So static friction has a maximum possible size, and an object will remain at rest as long as the static friction force is less than F sub max. It will just begin to slip when F sub s is equal to F s max, and a static friction force greater than Fs max is not physically possible. There's an equation for SF max. It's mu sub s times n, where mu, the Greek letter mu, sub s is called the coefficient of static friction, and n is the normal force of the surface on the object. If an object is sliding along a surface, there's a kinetic friction force which is proportional to the amount of the normal force. So there's an equation for kinetic friction is mu sub k times the normal force. And mu sub k is called the coefficient of kinetic friction. Kinetic friction is in the direction opposite to the object's velocity. So here an object is moving towards the right. It's also accelerating towards the right because the kinetic friction force is less than the pushing force. And it turns out that for any particular pair of surfaces, the coefficient of kinetic friction is less than the coefficient of static friction. So if you slam on the brakes of the car so hard that it starts skidding and screeching along, then this would be kinetic friction of your wheel on the road. Under normal driving conditions, the tire is rolling so that as it rolls, the bottom portion of the rolling wheel that contacts the surface is stationary. It's not sliding. So if you're speeding up with your car or turning or decelerating, it's actually static friction of the road on the wheels that provides the net force which accelerates the car. Now a car with no engine and no brakes on actually does not roll forever. If you just let a car coast on flat ground, you'll notice that after a long time it'll slow down and stop. This is true for wagons, it's true for a soccer ball. Anything that's rolling will have two things happening. One is molecular bonds between the surfaces will form and break as it rolls, and also the wheel will usually flatten a little bit and deform, which will create heat. So this is called rolling friction. there is an equation for rolling friction which is mu sub r times n, where mu sub r is called the coefficient of rolling friction. And the rolling friction is like kinetic friction. It's direction opposite to the velocity of the rolling object relative to the surface. So here's some actual coefficients of rolling friction that we've measured experimentally. If you have rubber on concrete, this coefficient of static friction is 1, kinetic friction is a little less, 0.8, and rolling friction is 0.02, very, very small. A steel surface on another steel surface where the surfaces are dry, 0.8, 0.6, and 0.002. This is why trains will roll so far even if there's no engine on, is because the coefficient of rolling friction of steel and steel is so small. If the surfaces are wet, steel and steel gets very slippery. Wood on another wood surface, or wood on snow, these are very small coefficients. Ice on ice, kinetic friction 0.03, very slippery surfaces have small coefficients of friction. So we have this model of friction. Actual friction involves the details of microscopic details of a surface, but experiments show that we can use these three equations, actually this is one inequality and two equations, to give a simplification of reality. Static friction must be less than mu sub s times n. Kinetic friction is equal to mu sub k times n, opposite the motion, and the rolling friction is equal to mu sub r times n. Here motion always means motion relative to the surface, and the forces of kinetic and rolling friction are proportional to the normal force of on the object. And the maximum static friction force is also proportional to the normal force of the surface on the object. Here is results of an experiment of pulling an object with a greater and greater pushing force and measuring what is the reaction friction. So as long as the pushing force is less than the maximum static friction, then there's this one-to-one relationship. As the pushing force increases, the static friction force responds and is the same until it gets to this maximum, then it suddenly drops down as the object starts moving. The object slips when Fs equals Fs max, and as the object moves, the kinetic friction force is constant even as the pushing force is applied. It no longer depends on the pushing force. So again, the cause of friction is that all objects are very rough on a microscopic scale. When two surfaces are pressed together, the high points from each side come into contact, and the amount of contact depends on the normal force. When the two surfaces are sliding against each other, the bonds never form fully, but they do tend to slow the motion and create heat. Okay, finishing off Chapter 6. Section 6.5 is on drag. So the air exerts a drag force on objects as they move through the air. Faster objects experience a greater drag force than slower objects. Here's a motorcycle. If it's going very, very high speeds, then the drag force in the motorcycle is significant, and it's opposite to the direction of the object's velocity through the air. For normal-sized objects on Earth traveling at a speed v, which is less than a few hundred meters per second, air resistance can be modeled as 1/2 c times rho times a times v squared, opposite to the direction of motion, where a is the cross-section area of the object. That means the area as measured in a plane perpendicular to the object's velocity. Rho is the density of the air, which turns out to be about 1.2 kilograms per meter cubed. And c is a dimensionless number called the drag coefficient. Okay, it depends on the shape of the object, but it's often sort of around 1. Example, if you have a smooth spherical object moving through the air, the cross-section is going to be pi r squared, where r is the radius of the sphere, and the drag coefficient is 0.5. If you have a cylinder falling end down, then again the cross-section area is pi r squared, but in this case, due to the shape, experimenters have found that the drag coefficient is 0.8. If a cylinder is falling side down, then the cross-section area is actually that of a rectangle. It turns out to be 2 times r, the radius, times L, the length of the cylinder. And a cylinder falling this way has a greater drag coefficient. Again, it's measured experimentally to be 1.1. So, as an object falls through the air, the drag force increases and increases as the object gains speed. If the object falls far enough and gets to a high enough speed, it will eventually reach a speed in which the magnitude of the drag force equals the magnitude of the force of gravity. So in this case, the net force is 0, so the acceleration will be 0, and the object will travel at a constant speed called the terminal speed, v sub term. Okay? And you can work out, and it's worked out in the text, that the equation for terminal velocity is the square root of 2 times the mass of the object times g divided by c times rho times a. So we plot here the vertical component of an object's speed versus time as it falls. The velocity starts at 0 if it's dropped from rest, and it becomes increasingly negative as it falls. Without drag, the velocity would versus time graph would be this straight line with slope a equals negative g. When drag is included, what happens is that it falls with less and less, or a speed which is increasing less quickly and approaches asymptotically out towards negative v term. The remainder of Chapter 6 is examples of using Newton's laws. Please read through section 6.6.